Today on Macaulay Math, we're evaluating limits. Intro. Hello, I'm Professor Macaulay, and this is Math 200, Lesson 3 on evaluating limits. Our goals for today: we're going to evaluate limits with properties of limits. We're going to develop strategies for finding limits. We're going to also evaluate limits using the dividing out technique, the rationalization technique, and the squeeze theorem. Last lesson, we used a formal definition to evaluate limits. This process is cumbersome at best. Mathematicians have developed properties of limits to simplify this process. These rules have been proven using the formal definition so that we can evaluate limits far more efficiently. So we have some properties of limits. And before we get started, again, I want to note that these properties are found using the results of the formal limit process learned in Lesson 2, and are intended only as shortcuts but not as proof. And so some simple limits that we have here: if you have the limit of some constant b as x goes to c, or this function is not defined in terms of x, so it will always be that b value. The limit as x goes to c of just the value x is going to be c, and the limit of x to a power as x goes to c is just going to be that c to a power. Additionally, we have some other properties of limits. If b and c are real numbers and n is a positive integer, let f and g be functions with the following limits. The limit of f of x as x goes to c is going to be this capital L, and the limit of g of x as x goes to c is going to be this k. And so the limit as x goes to c of b times some function is going to be b times that limit. The limit as x goes to c of the sum or the difference of two functions will be the sum or the difference of the two limits. The limit as x goes to the c of the product of two functions will be the product of the two limits. The limit as x goes to c of the quotient of two functions will be the quotient of the two limits, provided that the denominator is not equal to 0. And the limit as x goes to c of a function raised to a power will be the limit raised to the power. So some examples that will use these properties. Given that the limit of f of x as x goes to c is 27, what is the limit as x goes to c of the third root of f of x? Now, I can rewrite this as the limit as x goes to c of f of x, all by changing the third root to the 1/3 power. And if we go back, the limit of a function to a power is just the limit to the power. And in this case, this limit is 27, so 27 to the 1/3 power is just going to be 3. If I have a function divided by a constant, that will be the same as the limit of a function multiplied by a constant. We'll just rewrite it as 1/8. So this thing I can rewrite. I can take this constant and bring it out front and say that this is 1/18 times the limit as x goes to c of that f of x. Now this f of x, we're given that it's 27. So we can say that this is 1/18 times 27. And then 27 over 18 both have a factor of 9 in it. This becomes 3/2. And that is our values. Some additional rules for finding limits involving direct substitution. The limit of any polynomial at c is the value of the function at c. This is called direct substitution. To find the limit of the function, if it's defined at this value c, whatever that might be, for the most part, we're just going to be able to plug in that c and get the limit. This is called direct substitution. The limit of any rational function. A rational function is the quotient of two polynomials. at some value c is the value of the function at c provided that the denominator is not equal to 0 at c. The limit of a radical expression at c is the value of the function at c provided that c produces a positive value under the radical for even roots. The limit of a composite function, the limit as x goes to c of f of x composed with g of x, is the function value of the limit of g of x. The limit of any trigonometric function at c is the value of the function at c, provided that c is in the domain of the trigonometric function. So let's do an example. So find the limit as x goes to 1 of this function here. And so first, I should note x squared minus 2x plus 3 is a polynomial. And since it's a polynomial, this first rule here says the limit of any polynomial at c is the value of the function at c, called direct substitution. That says, thus, we can evaluate the limit through direct substitution. And this thing is just going to be equal to 1 squared minus 2 times 1 plus 3. So 1 minus 2 is negative 1 plus 3 is 2. So we want to evaluate this limit. And the first thing I should note, if we try a direct substitution, we will get 0 divided by 0. This is called an indeterminate form. All right. And again, anything divided by 0, even 0, is undefined. All right. So what we're going to use, the dividing out technique. And what the dividing out technique allows us to do is to divide each term by x squared. Now notice, x to the 4th, 5x squared, and x squared all have a factor of x squared. So since they all have a factor of x squared, we can divide that out. So we're going to do that. And I haven't taken the limit yet. I haven't evaluated it. So I still have to write it. But x to the 4th divided by x squared is just x squared. And then negative 5x squared divided by x squared is just negative 5. And then x squared divided by x squared is 1, but we wouldn't put anything over 1. All right, so another note. This is not the same function, but the limits are all the same. So we've taken an indeterminate form and we've changed it into a form that we can evaluate. And so now this is a polynomial function, and do the direct substitution, which will give us 0 squared minus 5 is equal to negative 5. And that's the value of that limit. As in the last example, if we were to use direct substitution, we would get another indeterminate form. Because if I plug in 0, I'm going to get a 0 here. I'll get square root of 2 minus the square root of 2 is 0. All over 0. So I have another indeterminate form. But again, that does not guarantee that the limit will not exist. So what we're going to try and do here is we're going to try and use the rationalization technique. And what the rationalization technique is we're going to multiply by a funky 1. And when you multiply by 1, the function stays the same, so we're not technically changing this function at all, at least not yet. And we're going to multiply by the square root of 2 plus x plus the square root of 2 all over the square root of 2 plus x plus the square root of 2. And I'm going to say here, recall that a minus b times a plus b is equal to a squared minus b squared. So we have the limit as x goes to 0, the square root of 2 plus x minus the square root of 2 over x times, and again, we're multiplying by 1 here. So here we're going to multiply by the square root of 2 plus x plus the square root of 2 over the square root of 2 plus x plus the square root of 2. All right, and so if you recall, we'll have a minus b times a plus b is equal to a squared minus b squared. I have not evaluated the limit yet, so I still have to write it. The limit as x goes to 0. All right, so a minus b times a plus b is a squared minus b squared. So the square root of 2 plus x squared will be 2 plus x, and the square root of 2 will be 2 all over. Now I'm not going to multiply here. I'm going to leave this because I think I want to get something to cancel out, which will be nice. And so I have the square root of 2 plus x plus the square root of 2. And so here, let's say that I am multiplying by the funky 1. And here I'm going to do some simplifying. And so again, still haven't evaluated the limit, so I have to write it. But plus 2 minus 2 will leave me with an x on the top, and I'll have an x on the bottom. I have the square root of 2 plus x plus square root of 2. And now here the x's divide out. So I'm also using the dividing out technique in this one. And so my x's cancel, and again, have not evaluated the limit yet. X goes to 0, but I'll have 1 over the square root of 2 plus x square root at 2. So at this point, you should be saying, okay, what has that got me? I still have an x in the denominator. But in this case, with the x in the denominator, if I let x go to 0, I will not get a division by 0 like I had in this case. So here I can evaluate this limit with direct substitution. And so what that allows me to do, and again, now I am evaluating the limit, so I don't have to write it anymore. It'll be 1 over the square root of 2 plus 0 plus the square root of 2. So 2 plus 0 is just 2, so I have the square root of 2 plus the square root of 2. This is 1 over 2 square root of 2, and we should rationalize our denominator and say that we'll go square root of 2 over square root of 2. That'll give me square root of 2 all over 4 as my final answer. All right, the squeeze theorem. If h of x is less than or equal to f of x is less than or equal to g of x for all x in an open interval containing c, except possibly at c itself, the limit as x goes to c of h of x is equal to L, which is equal to the limit as x goes to c of g of x, then the limit as x goes to c of f of x exists and is equal to L. So what does that mean? Well, let's look at a video demonstration here. In this example, let C be a value in some open interval for which we wish to find the limit for some function f of x, as shown in the blue curve. Now, we can visualize a limit for L. For this function, But let's say that we cannot calculate that limit for f of x at c. One way that we can do this is by showing that there is a function g of x that is always above f of x and a function h of x that is always below f of x over our open interval. If we can squeeze the two outer functions together and force both g of x and h of x to have the same limit L as x approaches c, then we can say that the limit of f of x is also L as x approaches c. Here what we're going to do is we're going to use the squeeze function to evaluate one of the special trigonometric limits. And the way that we do that is we are going to squeeze the area of a sector in between the area of two triangles. So let's look at this diagram that I have right here. I have this big triangle right here, this big black triangle. It has a base of 1, and the angle here we're going to call x. So let's figure out what the area of each of these, and so we have this large triangle has a base of 1 with an angle x. We have a sector, so that's going to be defined by this blue curve. So think of this as a piece of a pie cut out from a circle. It's clearly always going to have a smaller area than the bigger triangle because it will never have this portion right here. Then I have this smaller triangle right here, and it will also be smaller than the area of the sector. It is also a right triangle with a right angle here, and so in this case the hypotenuse is 1. And so we can calculate the area of each of these values, and if you would like me to do that, I can do that during the class time. But the area of the big triangle turns out to be the tangent of x over 2, which will always be bigger than the area of the sector, which is going to be x over 2, which will always be bigger than the area of the little triangle, which we can calculate to be the sine of x over 2. We're going to try and get the limit of these two outer expressions to equal the same value, and therefore squeeze this middle one to equal the same value. Now, I know you might be saying, I thought we were trying to evaluate sine x over x. Well, we will get there, I promise. So the first thing that we're going to do is we're going to multiply everything by 2 over sine x. And so when I multiply by 2 over sine x, let's do this tangent one first because that one's a little bit harder to see. So let's go over to here, and we're going to go the tangent of x over 2 times 2 over the sine of x. And so my 2's cancel, and so that'll give me the tangent of x over the sine of x. And remember that tangent is sine x over cosine x all over the sine of x. And so my sines are going to cancel and leave me with the cosine of x. So if we go back to here, after I multiply this thing by 2 over sine x, I'm left with 1 over the cosine of x, and that will be less than or equal to, well, if I multiply 2 over sine x times x over 2, my 2's will cancel, and I'll be left with x over the sine of x. Now when I multiply the area of the small triangle by sine x over 2, and I get 2 over sine x, the 2's cancel, the sines cancel, and I'm left with just 1. So now what I'm going to do is I'm going to take the reciprocal of all of these fractions, and when you do that, the property of proportion says that I must change the sign. So when I make this cosine, it's going to be cosine x, and it would be over 1, but I don't need that. And then I will change the sign to make it less than, and this will be the sine of x over x, and that'll be less than or equal to 1. Now you'll see that we're getting to this sine over x that we're looking for. So now we're going to take the limit of each of these. The limit as x goes to 0 of cosine x less than or equal to the limit as x goes to 0 of the sine of x over x less than or equal to the limit as x goes to 0 of just 1. All right. Now, if we're doing the limit of cosine x of any trig function, the cosine of 0 exists, and so I can do a direct substitution for this one, and the cosine of 0 is 1, and we're trying to evaluate the limit as x goes to 0 of the sine of x over x, and the limit of any constant is always the constant, so that is going to be equal to 1. So what we have done is we have squeezed between two limits equal to 1. And again, we know that it's between it because the bigger triangle is bigger than the area of the arc, which is bigger than the area of the smaller triangle. So we squeeze these two together to get 1, and therefore we can conclude that the limit as x goes to 0 of the sine of x over x has to also equal 1. Now from that, we can have a couple of conclusions. And the first conclusion is we already know that special trigonometric limit, the limit as x goes to 0 of sine x over x is equal to 1. And with a similar proof, which you can look up on your own if you wanted to, the limit as x goes to 0 of 1 minus cosine x over x is equal to 0. So a quick example before we finish up. We want to evaluate the following limit here. So what I want to do is, clearly this is undefined as x goes to 0, so I have to have a different technique. And I'm going to ask you to again recall that the tangent of x is equal to the sine of x over the cosine of x. And so again, I haven't evaluated the limit, got to write the limit. And then I'm going to ask you to recall that when you divide a fraction, if I go a over b divided by c over d, that's going to be equal to a over b times d over c. So you take the reciprocal of the denominator and then multiply. So again, haven't evaluated the limit yet. Have to write it. But I can rewrite this as the sine of x over the cosine of x times 1 over x. All right. So since it's multiplication, I'm going to commute the cosine x and the x. So since a multiplication, you can multiply in any order. 5 times 2 is the same as 2 times 5. Haven't evaluated the limit yet, so I still have to write it. But I'm going to make this sine x over x times 1 over the cosine of x. The limit of a product is the product of the limits. So I am going to say that this is the limit as x goes to 0 of sine x over x times the limit as x goes to 0 of 1 over the cosine of x. And so the first limit is a special trig limit. And we saw that in the last slide. The limit as x goes to 0 of sine x over x is 1. And the second limit can be evaluated through direct substitution. And so This one is 1. And then when I let x equal 0, the cosine of 0 is 1. 1 over 1 is 1. So this is just 1. All right there, folks. I know that's a lot. That's all I got for today. So, the Star Wars fun fact of the day. In Rogue One, a Star Wars story, during the final battle above the planet Scarif, the X-Wing pilot with a call sign of Red 5 is shot down, allowing Luke Skywalker to have it during the Battle of Yavin in Episode 4, A New Hope. So there's fan service galore in Rogue One. That's all I got, folks. Have a good day. Goodbye.